Okay, so this video is about energy and chemical bonds. It's a little bit of a diversion from the Lewis structure stuff we've been doing, but it is definitely part of the material for this unit. Okay, so in this I'm going to talk a little bit about how covalent bonds form, and in doing so talk about the energy associated with that process and associated with a covalent chemical bond itself. So if we imagine that we are going to look at the potential energy of a covalent bond as a function of its internuclear separation, that is how far apart the atoms are, we would get a curve that looks something like this. So essentially at very short distances the energy is very high, okay, and then there's an intermediate range where the energy is lower, so this is the bond minimum. And then out here, as the internuclear separation increases, it goes out to some limit, which we're going to talk about, well, right now. So as always with a graph like this, we are free to choose the reference energy of E equals 0 anywhere we want to put it. And so here we choose the limit that this approaches as the atoms get infinitely far apart. And we're going to define that as our zero of energy. And so any energies higher than that are going to be positive, any energies lower than that are going to be negative. Okay, so now let's talk about imagining a chemical bond forming from atoms that are initially very far apart. So when we're out here in the limit, these atoms are so far apart that they're essentially not interacting with each other. The energy of the two atoms is just the energy of the two atoms, and the energy of their interaction, which is what we're actually plotting here, the potential energy, hasn't started to be different from zero. So then as we move them closer together and we track along this curve, the energy, they start to feel each other. They start to have an interaction, and that interaction is stabilizing, so it becomes lower than zero, right? Anytime we talk about an energy that is stabilizing, basically it's a stabilizing energy. The atoms are experiencing a net good interaction with each other, and so the energy is going down. And so we would talk about that here. So if we imagine it in some intermediate stage here, at this point on the curve, the atoms have gotten closer together and they're starting to feel that attractive interaction with each other, that stabilizing interaction. If we then follow the curve all the way down to the minimum, there's going to be some optimum distance here where the atoms are just the right distance apart so that they can have their best, lowest potential energy down here. Okay? And then if we were to force them closer together than that, then we would essentially be trying to push the atoms into each other. And that's a very, very difficult thing to do. And so that's why the energy goes shooting up, like we see here on this inner part of the curve. Okay, so if you tried to push them, basically that energy would rebound and the atom would come back to this most stable state. So essentially, you can think of a covalent bond as an optimum between the stabilizing this attractive force that the atoms feel as they get closer together and the repulsive force that they feel when they get too close together. And every pair of atoms is going to have some best value, which is represented by this state right here, where they're just the right distance apart and therefore have the most stabilizing energy. And of course, these are negative energies, right? We would represent these as negative. The process of forming a bond is therefore going to be exothermic. If we take a bond, take two separated atoms, and they form a stabilizing interaction, well, the whole reason that they do that is because we know in nature things want to lower their energies. Exothermic processes are generally favored. Okay, so now let's talk a little bit about some of the numbers associated with this. So this, for example, if we consider the simplest case of two hydrogen atoms, each with one electron, as they approach each other from that infinite distance and they sort of undergo this process of forming a covalent bond, they are going to come to a best case, a minimum distance of 75 picometers, and that's going to correspond with 432 kilojoules per mole of stabilization. Okay, and so, oh, by the way, there is a table on page 374 of your book that has these bond energies, and there's another table on the same page that has some representative bond lengths if you want to look them up for bonds that we're not going to talk about in today's presentation. Okay, so hydrogen is a pretty small atom. It's in the first row of the periodic table, so that means that two hydrogen atoms can get pretty close to each other when they're forming a covalent bond, and that 75 picometers is about the shortest value you're ever going to see for a bond length. And the bond energy 432 is one of the highest energies you're going to see for a single covalent bond. Now, so that length, like we said, is the distance between the nuclei at the bottom of the well. The energy released by the bond formation is one way of thinking about the bond energy, and of course that's exothermic, right? The previous page we talked about it. As the bond forms, that energy is released out into the world. It gets to a more stable state inside the system, and we think about that as an exothermic or a negative energy. On the other hand, if we're going the other direction and we wanted to separate those two atoms back to the free state and completely break that covalent bond, we would need to put in 432 kilojoules of energy. And so the sign convention is the same. We think of forming a bond as being associated with a negative energy and breaking a bond to be associated with a positive energy. The values in the table by convention are reported as positive. So you can think of those as kind of an absolute value. That's the quantity of energy that's going to be exchanged when you're either breaking or forming the bond, but you actually have to think about which direction you're going to properly assign the sign for the energy change in the process. Okay, let's look at some others. So here, if we go down to the second row with one of the atoms and make a carbon-hydrogen bond, you can see that because the carbon atom is quite a bit bigger, the bond length is quite a bit longer. The bond energy in that case is similar. Okay. Now, if we go to carbon and carbon, we can see the next thing that we're going to talk about. I did want to make one other point, which is that tabulated values here are averaged over a range of commonly occurring compounds. I don't want you to get the idea that every single carbon-hydrogen bond is 110 picometers long and every single carbon-hydrogen bond is worth 413 kilojoules of energy. That's not the case. That is an average value over a wide range of commonly occurring compounds. Carbon-hydrogen bonds are one of the most commonly found bonds in organic molecules. There is a bewildering arrangement of possible ways you can get carbon-hydrogen bonds in molecules. And so this is just an average value taken from some commonly occurring compounds. All right. If we go on and we talk about carbon-carbon bonds, we can see the next trend, which is that you can have carbon-carbon single bonds, carbon-carbon double bonds, and carbon-carbon triple bonds. And if we look at the trends, you can see that the carbon-carbon single bond is actually pretty long, and it has a bond energy that's lower than either of the two we've seen before. If we then extend it out to the carbon-carbon double bond, now the bond has gotten shorter, and the bond energy has gone up. And that gets even more pronounced for the carbon-carbon triple bond. The bond is the shortest yet, and the bond energy is even higher. This is general, and it makes sense. Multiple bonds are shorter and stronger than single bonds. Essentially, when those two atoms have formed their bond, there are more bonding pairs of electrons helping hold them together, and that means that overall you get a tighter bond, and it pulls, because it's tighter and stronger, it pulls the two atoms closer together than they would be if there was only one pair, if there were fewer pairs of electrons bonding the two atoms together. Okay, and we can see the same thing for carbon-oxygen bonds. A carbon-oxygen single bond is about 358 kilojoules per mole, and the bond length is 143. When we add that second bond for the carbon-oxygen double bond, the bond length goes down and it almost doubles the energy. And actually, there's another point that we need to make here, which is that sometimes when you have a particular compound that has a noticeably different bond energy, you're going to tabulate that one differently. You're going to tabulate it separately and keep track of it, particularly when that compound is very important. And the best example of that is carbon dioxide. The CO double bond in CO2 is shorter and stronger than the CO double bonds that you find in organic molecules, and so we keep track of it separately. We basically say that that's so important. Combustion is an extremely important reaction, and it's one of the ways that these bonds are used most often is to figure out enthalpies for combustion reactions, and I'll come up with how to do that in just a second, that we keep track of it separately, and its value is significantly higher than carbon-oxygen double bond found in other places. Okay, here are some other values that we're going to need in the course of this presentation. Okay, the last topic that we're going to talk about here is how to use these values to estimate enthalpies of reactions. So reaction enthalpies can be estimated by just taking the difference in energy between the bonds formed and the bonds broken, right? So you can think of having the reactants on one side. If you break all the bonds in the reactants to separate the atoms, and then you were to put them all back together to form the new bonds that you get in the products, well, both of those have associated energy changes. Breaking the bonds requires energy, forming them releases energy, and we can simply calculate the difference between the bonds broken and the bonds formed. And writing the equation this way preserves this exothermic endothermic sign convention that we've gotten used to in the course. All right, so let's do an example of how to do this on the next page. Okay, so we're going to do a familiar reaction. We're going to look at the combustion of methane. Now here is a balanced chemical equation with an actually looking at the diagram so we can think about the bonds. CH4 has 4 carbon-hydrogen bonds, methane, and then there's 2 oxygen-oxygen double bonds here for the 2 O2 molecules. And then we're going to have different bonds. Here's those CO2 carbon-oxygen double bonds I was talking about, and then we're going to form 4 oxygen-hydrogen single bonds in the 2 water molecules. Okay, so following our playbook, if we look at the reactants, we can look up the standard enthalpy of reaction here is negative 808 kilojoules. Okay, so if we look at what we need to do to the reactants, we need to break all the bonds in the reactants. There's those 4 carbon-hydrogen bonds and the 2 oxygen-oxygen double bonds, and that gets us to the separated atom reference state. Okay, so we've got now just 1 carbon, 4 hydrogens, and 4 oxygens, and we're now going to put them back together, and the process of getting there cost us 2,642 kilojoules to break all those bonds. We're now going to form the bonds in the products, and so now we've got those 2 carbon-oxygen double bonds and the 4 single bonds in the 4 OH single bonds in the waters, and that gets us back more energy than we had to put in to break the bonds. It gets us back negative 3,450 kilojoules when you add up all those bonds, and the difference, not surprisingly, is the difference in the enthalpy of reaction of the reactants and the products. So this is just another example of how we can use Hess's law to calculate an energy the way we want to, rather than having to worry about the direct process. It's important to realize that no reaction actually goes this way. There is almost always a better path than breaking all the bonds at once and forming all the new ones. But that doesn't matter. The fact that this process never happens and is totally imaginary is fine by Hess's law. We're free to choose because enthalpy is a path-independent state function. We're free to choose any reference state that we want, and getting into the reference state is basically the breaking all the bonds, and getting out of the reference state to the products is forming all the bonds. This is similar to what we did with enthalpies of formation in Unit 6, in the unit on thermochemistry. We went from the reactants to the elemental reference state, and then we went from the elemental reference state to the products. This is similar in approach, although you have to be a little careful because we use the opposite sign convention. Okay, I now strongly suggest you go straight to the discussion question, because in the discussion question I ask you to go through an example where you have to apply this new technique for estimating bond enthalpies in order to do a calculation.